to this new seminar of our series for the INAF Observatory of Abruzzo. Today the speaker is Arthur Choplin. Arthur obtained his PhD in astrophysics at the Geneva Observatory in 2018, working on nucleosynthesis in the first stellar generations. Then he moved to Japan for a postdoctoral position and came back to Europe to the University of Brussels, where he has been working since 2020. And his research interests are stellar evolution and nucleosynthesis from the low to the high mass domain. And today we will talk about the intermediate neutron capture process in HMB stars. So Arthur, you can start the seminar. I will let you know 5 minutes in advance when the time is finishing, and you will have 45 minutes. So please.
Yeah, thank you very much. Hello, everyone. So I would like to thank you, Diego, for inviting me, and also the organizers, and to invite me to present, to speak a bit about the I process, the intermediate neutron capture process, and I would say mostly in what we call AGB stars, but yeah, I will also try to be a bit more general. This is globally the plan. I would like to spend about 15 minutes on each of these parts. And first, I would like to give you an maybe incomplete overview of the SR and I processes, so the basic workings, the sites, the observational motivations. Then speak about the AGB stars and the S and I process in AGB stars, and then a bit more about the I process in AGB stars. So maybe the big goal of nuclear astrophysics is to try to understand how we can have gone from here, so the periodic table just after the Big Bang, to the periodic table today with all these elements. And the big questions probably are how, where, and when were these elements synthesized. So how, by which processes, stellar fusion, neutron capture, whatever, where, in which sites, neutron star mergers, supernovae, etc., and when, at which stage of the universe. And for that, I would say we need to rely on different fields. At least I can see 5 boxes, including nuclear physics in the theoretical and experimental sides, then astronomical observations, of course, and astrophysical site modeling, and also on the top maybe galactic chemical evolution modeling. And there are many connections between these boxes. Of course, and here in Brussels, we are mostly working on, there is a team working on observations, I would say, a group on nuclear and atomic physics theory, and I'm on the astrophysical site modeling group, mostly. Okay, so coming back to this plot, we, I think, agree to say that almost all of the heavy elements, trans-iron elements in the universe were synthesized by neutron capture processes. So not all, but almost all. And here is one of these neutron capture process, which is the slow neutron capture process operating at low neutron density, so 10 to the 5, 10 to the 10 neutron per cubic centimeter in relatively long time scales. And here you see, I don't know if you see the pointer here, but my pointer, but this is like a nuclear chart with number of proton and neutrons. And this is the basic working of the S process. Many of you know this very well, but yeah, I will try to be quite pedagogical. You see the stable isotopes in black, and you start at some point with an heavy seed, like the I1, which can be abundant and which has a quite big cross-section. And at some point, you have free neutrons in the stellar medium, and you can capture some neutrons and synthesize a heavier, neutron-richer isotopes until you reach an unstable element, and then you have beta decay, then capture another neutron, beta decay, etc. And you follow like this path, which has some branching points, but this can be called the S process path, which really sticks to the value of stability. At the other extreme, you have the R process, rapid neutron capture process, which goes much more to the right, to the neutron-rich side. You have much more neutrons. The time scale is much shorter. And the I is just in between. So the I process for intermediate, it was called like that because it's intermediate in terms of neutron density and time scales, I would say, in between the S and the R. So So you have a typical I process path in green here. Each of these processes will leave a distinct chemical fingerprint. And of course, a question that I would like to address next is what are the sites for these processes? So where these processes can take place. So for the S process, the common agreement is to say that it happens mostly in AGV stars. I will discuss these stars later. Asymptotic giant branch stars, which corresponds to the end life of 1 to 8 solar mass stars. And also in massive stars during the core helium burning phase, and also shell carbon burning, but mostly during the core helium burning phase of massive stars. The R process needs more explosive events, like explosive environment. The main site would be probably neutron star mergers, and also it was suggested that it can develop in some peculiar supernovae like collapsars or magnetorotational supernovae. And very recently also, another site was suggested, which are magnetars, the giant flares in magnetars. So yeah, in this case, the sites are a bit more extreme, I would say. We need like some extreme environments. So what about the I process? First of all, I would like to show you this plot that shows the number of publications as a function of year for related to the I, S, and R process. So you see that the S and R processes are much more, I would say, discussed and much more present in the literature, I would say. But you see that also that the I process is quite growing lately. It attracts more attention, I would say. It's quite recent as well. And of course, it's much smaller than the S and the R process in terms of discussion in the literature, but just to show you that it's not a completely obscure and weird process that nobody is interested in. It's not so recent, actually, because already in the 70s, you have these two papers from Starfield et al. And also Cowan and Rose in the 70s that mentioned the possibility of this I process. This is the abstract of these two papers. And for some reasons, probably linked to the observations that were not enough, or some reasons, it didn't attract a lot of attention. And as you can see in this plot, it really started around 2010 or 2015, I would say. But not a lot of actually no work, really, I think no work, to my knowledge at least, on the I process before this time, except these two papers that just suggest the possibility of this I process. Okay, so the I process, and this is, I think, to me, like a kind of definition that could be used, is it can happen when some protons or hydrogen is mixed into a convective helium burning zone. So you have a pan here with the helium which is boiling, and you put some hydrogen, and you might here get actually the I process if you do that. So you have to mix this hydrogen into a convective helium burning zone, and we have in this case what we can call a proton ingestion. So there are many alternative names. I don't know what is the best name, and I will use proton ingestion, but just to let you know that. And this is very relevant as well. We can call it hydrogen flash, for instance, or we can also find a dual shell flash, or also longer names like helium flash driven deep mixing, and so there are different names. But I will use proton ingestion for this for today. So this is a very rough and schematic picture of a star. You have the core and the helium shell, hydrogen shell, and stellar envelope. And globally, what you need to have the I process happening, and you need to mix actually these two layers, the green one with the purple one. And if you do so, you may get this I process nucleosynthesis. So you need to take some protons in the green zone and to put them into the helium shell, convective helium burning shell. So I process, this is maybe one message, I process requires a proton ingestion event, I think. These are, I think, the possible sites. I try to be quite exhaustive, but I might have missed some works. But the possible sites that were identified for proton ingestion or I process, and there are quite a lot. There are at least 5 sites, I think. It includes AGB stars. This is the site we are working on in Brussels, but there are many other works, especially also in Italy, from Cristallo, I think. But in in Japan as well. Different people are working on these sites. Accreting white dwarfs. There is this is like at some point, I will not go into details on the sites. First, I don't have the time, and second, I'm not really aware of the details of these sites, but I know that, for instance, there is many work by the Canadian group, Pavel Denisenkov, Volker Wig, also Luciano Persanti, that studied the fact that at some point, if the white dwarf is in a binary system, it can accrete some material from a companion, and you can have in these systems proton ingestion and eye process. There are also massive stars during the last living stages, possibly also during the choroidal flash of low mass stars, and also in post-AGB stars during the very late evolution of these low mass stars, so just before the white dwarf phase. These are in green the works that follow high process nucleosynthesis, so that include a large network. So many works just follow the light elements, which is already very interesting, and you can see that the effect of what's happening when you put some protons into like a convective helium burning zone. You will see that it can really change the structure of the star. But there are not so many works, but there are more and more, but not so many that really follow the extended nucleosynthesis, and especially the high process nucleosynthesis. So there is a need for such models. And this is what we are trying to do, among other, in Brussels. I would like to spend some time on the motivation and try to convince you a little bit why do we need this high process. So if you look at the chemical composition of the sun on the right, the sun is an integration of many previous events. And you have a schematic picture on the left. It was made in a reservoir that was enriched by many previous stars, neutron stars, whatever, supernovae, etc. And what we see here is it reflects like an integration of many previous events. But still, we can, of course, see some very interesting features. And for instance, these are these peaks here, which can very well explain by S and R process nucleosynthesis. These peaks around xenon, barium, lead, for instance. I will not go into details, but yeah, we can already see some very nice features, of course, in the sun. But what is, I think, to me interesting, at least, is if you go to stars which are much more metal poor than the sun, it's quite interesting because if you look at the stars which are very metal poor, they are very close, or quite close, I would say, to the first stars. And you don't see, when you look at the chemical composition of a metal poor star, you don't see an integration of many previous events, but just a few previous events, or even maybe just the first stars in the most extreme cases. So in these metal poor stars, you can probably more see a bit better identify the individual nucleosynthetic processes. So this is an example of a S process star. It's a quite old paper, but anyway, this is, you see here the y-axis is showing the abundances of relatively to the sun in log scale. So L is for element over iron, normalized by iron. The line is showing an S process AGB models, 1.5 solar mass, and the dots corresponds to a low metallicity star, a metal poor star that was observed in a few years, maybe decades ago, maybe 2010 or so. And you see here that the fit is quite reasonable. So the models the S process AGB can explain quite well the observed star. This is an R process star with two models, a neutron star merger in orange and the blue. You have a specific magnetorotational model. And here again, of course, it's not perfect, but it was suggested that these black dots, which is an observed R process star, can be explained by an R process model. So this is just to show you that some stars have a chemical composition which is compatible or almost compatible with S or R process models. But there are some stars that don't. And here is just one example of one star, which is a metal poor star, and which are represented by these dots here. And the red line is showing the best S-process models I can get, at least, if I try to reproduce the chemical composition of this star, which was observed by Aoki et al. Yeah. But you see that there are some problems. So, for instance, for these light elements around strontium, it's difficult to explain the low abundance of these elements, the europium, the erbium. There are many elements that cannot be reproduced. So if you look, you do the same exercise with an R process model, you have the blue curve, and still you have some problems. So you cannot reproduce well this star with an S or R process model. You might think of a mixture between S and R, and this was already done in the past. You can say, okay, maybe if I combine S and R, I can reproduce this star. And indeed, you can do better. So you look at the chi-square. So this is the quality of the fit. If you do with S process, it's about 5, R process about 7. If you make a combination of S and R, you have something about 3, which is not bad, but still there are some elements that cannot be explained very well. And if you take an I process model, in this case it's an AGB star, at 1 solar mass star, you can reach much smaller value for the chi-square value, which means that the fit is better. So at least in this case, for this specific star, it's not many, it's just one star, but the I process is providing an interesting solution. And yeah, the surface chemical composition of this star cannot be explained by the S and R process, and I process is a possible solution. So to summary plot, here you have about 15 stars that might be I process stars, and you can see on the x-axis the smallest chi-square we can get using an S process model in black, R process model in green, and I process model in red. And you see that for these stars that might be I process stars, the I process is indeed giving in general a rather good solution. Instead, but if you look at the S and the R, it's not very, I would say, the solution, it's not very acceptable. The chi-square is a bit high. And if you try with a combination of R plus S, you can get something which is not really bad, but not, I would say, as low in terms of chi-square as the I process model. So this is giving some credence to the existence of the I process, I think. And there are other evidence is maybe a big word, but other hints of the existence of the strong hints of the existence of the I process in presolar grains, in clusters, in the Sakurai object. You can check this paper from Foltervik, for instance. Also, it was suggested that some signature of I process could be seen in the solar system composition. In this paper from Benoît Côté in 2018. Okay. I will go to the second part and try to explain you or try to discuss a little bit these AGB stars. Okay, so as I said, these AGB stars corresponds to the end of life of low and intermediate mass stars between 1 and 8 solar masses. During this stage, there is a complex interplay between nucleosynthesis and mixing. And there is also strong stellar outflows and winds. So the schematic picture of an AGB star is like that. You have in red the big convective envelope, and in the center you have the core. If we zoom in, we see the carbon-oxygen core, the helium burning shell in blue, intershell in purple, and then above you have this hydrogen burning shell in yellow. So there is 2 burning shells which actually burn alternatively, but yeah, on the top of the carbon-oxygen core. So something I want to mention, which is I think really interesting, is that some AGB stars show technetium line in their spectra, and the thing with technetium, which is interesting, is that it has no stable isotopes. So if you look at the nuclear chart here, you have the technetium, and the black squares are stable isotopes. The technetium has no stable isotopes, and the longest lived isotopes is technetium-99, which is 2×10⁶ years, which is smaller than the stellar lifetime, quite small compared to the lifetime of a low mass star. So this means that if you see technetium in a star, at the surface of a star, it has to be made now in the star itself. It cannot come from previous generations, from ancient stars that lived before and then reached the interstellar medium in which the new star formed. It has to be made in the star. And this is why this is a kind of proof that there is ongoing heavy elements nucleosynthesis in AGB stars. But how? How does it work? So we don't. I think that we don't really know actually. That there are many very good models and works on that, but it's still it's still an open question. And of course we have many hints and many good possibilities, but to me it's still we still don't really know how it works. So of course, to answer this question, we need, because the stars are 3D objects, we need to model the stars, and we need to model them in 3D. But this is not possible, however, because it exists stellar evolution codes in 3D, but the thing is that you cannot model the entire life and scale of the star in 3D. It's not possible. Even in the near future, it won't be possible, probably. Of course, the 3D models are very nice because you can really model, have a proper modeling of the 3D processes like convections, but they are too expensive computationally. And it's the same for 2D globally. So the only way we have to model the full life and scale of stars, and also to follow the full nucleosynthesis, is to go 1D. Maybe the most well-known code is MESA, but there are many other codes in 1D. And the bad thing with 1D models is, of course, we have to assume spherical symmetry and use simplified theories for 3D processes like convection. So in 1D, you divide your star in shells, thousands of shells. You solve the stellar structure equations, and you include some important ingredients like nuclear reactions rates, mixing, mass loss, opacities, any kind of these ingredients. And I have to say that these codes are widely used because one reason, I think, is that even if there are, of course, approximations, I would say I think that the observations in general confirm the general picture of stellar evolution predicted by 1D models. So even if these 1D models are wrong, I would say, they are not completely wrong, and in a sense, they are not so far, I think, from what's happening in nature. And this is, I think, something of course, there are some discrepancies, and but they are not so far from real stars, I think. Let's take a 2D slice of an AGB star now. So you again have this carbon-oxygen core in yellow, these two burning shells in blue and green, and the convective envelope. So you have the two burning shell on top of the carbon-oxygen core. Something that is very convenient is to go 1D. So you have this plot here, which is called the Choplin diagram, and you see the time evolution of the AGB star with the time and the radius, the y-axis. So you still have the two shells, the core and the envelope, and here you have these convective thermal pulses, which are thermal instabilities of the helium shell, or kind of flashes that occur at regular intervals. And these are kind of very robust features of all AGB models. So how does the S process is developing in such stars? So this was explored by many different in many different works. And so the idea is that you have at some point below the envelope, you need to add, I think in all works, it is like that. You need to add some kind of mixing, for instance, overshoot, that will diffuse a little bit of protons contained in this large convective envelope in gray, a bit below, and you can form like this a C13 pocket that can trigger the S process thanks to the C13 alpha N reaction at a temperature of roughly 100 million degrees Kelvin. So the S process elements are really synthesized here during a time scale of, let's say, 10 to the 4 years. here in this red region, and they are engulfed in the next convective pulse here, where the mixing is very efficient. So this pulse becomes enriched in S process elements. And later on, when the pulse is, I would say, vanishing, this part of the star here in red is rich in S process elements, and the envelope is going down and will dredge up some of these elements up to the surface and enrich the surface in technetium, strontium, barium, etc. Again, I know some of you know this very well and even better than me, but I think it's, I wanted to do something quite pedagogical. So yeah, I apologize if many of you know this very well. But yeah, this is how you can enrich the surface of the star in technetium, in strontium, in many heavy elements, thanks to the S process. There is also another kind of S process which can happen at the bottom of the thermal pulse at higher temperature, 300 million Kelvin roughly, in massive AGB stars, thanks to the neon 22 alpha N reaction. These are the two kinds of S process, I think, the radiative one, I would say, this one, and the convective one. So there is another way of synthesizing heavy elements in AGB stars that was identified. It's the I process. So how does it work? It was shown quite early that in some cases, the entropy barrier here, in this at the bottom of the hydrogen burning shell, I would say, which is represented here in green, can be surmounted by the energy released by the thermal pulse. And in this case, we have a proton ingestion or a hydrogen flash, but I use the term proton ingestion here. So this is the structure evolution of a 1D AGB models with proton ingestion. So this is without. This is the standard view, I would say. Of course, it's schematic, but it is, if you look at a real model, it will happen mostly like this. And this is with the proton ingestion. So the first thing you can see is that the structure has changed. And this is because there is a lot of nuclear energy released by some reactions, and this modified the structure of the AGB, the structure of the star. So what's happening is that you have some protons which are represented here in green, which are transported down in the pulse, burned quite quickly by this reaction, C12P gamma to the nitrogen 13. And the nitrogen 13 will beta decay in about 10 minutes into carbon 13. And the carbon 13 will burn at very high temperature, quite high temperature at the bottom of the thermal pulse. And this is really here in this purple region that the I process will take place. And then later on, because of convection, here the mixing time scale in the, I would say the convective time scale in the pulse is about 1 hour. So it's quite quick. The convection will bring these freshly synthesized I process elements up to the surface. And then, of course, it depends on many parameters, especially mass loss or whatever, but the standard AGB phase can resume with further S process, further convective S process. And so to summarize, there are 3 modes of production of heavy elements in AGB stars that were identified. The radiative S process, convective S, and I process. And each time either the reaction is different, the main reaction giving the neutrons, or the temperature is different, you see, and it leads to different neutron densities, typical neutron densities. The thing is that combinations are possible. It's not either I or S. You can have in some case just I or S, I think, but I plus S is also possible. So they can develop in the same AGB star. And of course, after that, this material, S or I, whatever, these heavy elements are ejected through stellar winds. And this is the first pictures on the first slide. This is like the ring nebula captured by the James Webb Space Telescope, which is very amazing, I think. And this is a dying AGB star, actually. The central star is a post-AGB star that lost its envelope, so it will soon become a white dwarf. And this reddish, yellowish material you see around is the material ejected by the AGB star. And this is really this material that might be, that can be enriched in nucleosynthesis, I think, in heavy elements, for instance. Okay, I'm going to the final part, which is I will discuss a bit more the I process in a bit more in details, I would say. And if we will look a bit more in details at what's happening here in the model. So in terms of nucleosynthesis. Okay, so just 1 second. So this is a part of the nuclear chart showing the I process in an AGB star at the bottom of the thermal pulse. In black, you see in red the main path of the I process, and the squares are colored according to the mass fractions of the isotopes. And in this case, we have a network, you need a network of about 1,000 isotopes to follow the I process, and that includes around 1,000 N-gamma reactions, roughly. In our case, we use different works, sources for the rates. NACRE, StarLib, TALIS, NuBase. The main point I want to make here is that in these 1,000 N-gamma reactions, there are about 75% that are only theoretical. So there are many rates that are not experimentally constrained. And this is why we rely mostly on theoretical rates computed by the reaction code TALIS here. And this is also why we really need to make these models inputs from nuclear physics, from theory and the experimental side. And these rates actually, which are relevant for the I process, are very difficult, I think, to be constrained experimentally, because we deal with isotopes which have very small lifetime. So and we are a bit far from the value of stability, so it's a bit difficult. But here there are some recent works, especially with the Oslo, beta Oslo methods. Probably there are other methods. I'm not an expert on that, but just to mention the fact that there are some works trying to really constrain experimentally some of these rates, especially here in these three works. It was the tin, the barium, and the nickel isotopes. Isotopes a bit rich in neutron, which are important for I process probably. And yeah, it's getting more and more possible to constrain these rates, actually. And in the future, I hope that this number of 75 will decrease to 50 maybe, or something like that. But yeah, it will take time. So where does this I process end? So where does this path is ending? This red path here. So it goes up, but where does it stop? Actually, it can reach the actinide region. So here you have like the upper part of the nuclear chart, and you see here the main path. I would say the main flux is going through this blue arrows, but there is a small part, at least I think 30 or 20% of the flux that can leak toward the actinides and synthesize very heavy elements like uranium and thorium. So the thing is that if you are below this neutron density, so let's say 5 × 10⁻⁴, it's not exact number, but this is a rough number. But if you are below this number in terms of neutron density, there is a cycle in the that will prevent the formation of actinides, of heavy elements, in a cycle in this region. So you will stay in the lead, bismuth, polonium region, and there is no thorium, uranium synthesized. So the cycle is broken if you go above this value, 5 × 10⁻⁴ roughly. And it's quite interesting to see that the I process is really taking place at this neutron density, 5 × 10⁻⁴, 10 to the 15, 10 to the 16 maybe, but it's really in this range of going just above the limit which is needed to synthesize the actinides. So to summarize, the S process is ending here, and it was shown by Clayton and Rosbach in the 60s already. There is a cycle here in the lead bismuth region that you cannot go further. Of course, the R process, you can go very, very high and synthesize super heavy elements, but it seems that the I process also can. And this is why I really want to emphasize that it is really thought that in general the actinides can only be produced by the R process during extreme events, but actually it can also probably be they can be synthesized with I process in AGB stars, but of course also in other sites, because there is just enough the number of neutrons is just enough to I would say to break this cycle and to synthesize these heavy elements. Another question that I wanted to address is the following one: at what mass and metallicity does this photon ingestion or I process occur? And this is important, for instance, for galactic chemical evolution modeling. When you do galactic chemical evolution, you want to know which stars will experience I process. So, does this 3 solar mass star experience I process? Like if you take solar metallicity, 2 solar mass star, does it experience I process or not? So this is something that I think is important if you want to study the evolution of the elements, especially the heavy elements. So this is a compilation of different works, and all dots are AGB models. You see the initial mass as a function of metallicity, and when the dot is empty, it means that there is no ingestion, so no I process, and when the dot is red, it means that there is I process, or proton ingestion. The sun is quite high here. You see the 1 solar mass star at solar metallicity. And you see that all models, so no matter the stellar evolution code or the input field, no matter the code, I would say, all these works kind of agree to say that there is a zone at low mass and low metallicity where there is proton ingestion, and where there is I process developing. So the I process, or the proton ingestion, happens in low metallicity, low mass AGB stars. And as shown in this plot, so this is because the entropy barrier at the bottom of the hydrogen shell, as I was mentioning, this kind of entropy barrier before, is smaller, is easier to cross at low mass and low metallicity. And this was shown quite early by Iben and Fujimoto in the 70s or 90s. But what I want also to show is that this zone in gray here is a kind of minimal zone. All these models that you have that are listed here does not include extra mixing. But if you include extra mixing, like overshoot, for instance, or maybe rotation, you can change this gray zone. So the very basic idea here is that I want to show is you have like the stellar radius, the time. So this is a kind of Kippenan diagram with the hydrogen-rich zone in green. You have the thermal pulse, and in this case, you don't have any connection between the thermal pulse and the hydrogen-rich layers. So there is no ingestion, no I process. But if you include some overshoot at the top of the thermal pulse, and generally it's quite common to include some overshoot in stellar models to try to better mimic convective mixing. In this case, you see that the thermal pulse is expanded a little bit, and in this case, you have some connection, and then you can maybe take some protons and trigger the I process. And the idea was to try to see how this impacts the occurrence, this overshoot impacts the occurrence of hydrogen ingestion and I process. So you have the minimal zone, and so this is without overshoot, without nothing, I would say. And if you put a little bit of overshoot, the zone can extend a little bit. So you go from the gray zone to the green zone. So the zone extends with these f-top parameters, which is just controlling the strength of the overshoot. So if you put more overshoot, you can have this blue region and this red region in case you put a strong overshoot, I would say. So this f-top value is unknown, and presently we don't know what is the right zone, but the right ingestion zone, I would say. Is it the gray one, or is it maybe the blue one, or we don't know. But this is just to show that the I process and proton ingestion can also, depending on this overshoot, develop at higher mass and at higher metallicity. Let's focus now on just one model. So this is a one solar mass star at low metallicity. And this is the chemical composition at the surface of the AGB star after the proton ingestion. So again, this is the abundances relative to the sun in log scale. And you see that some elements are synthesized by the eye process. So this is like an eye process model, I would say. So you have a lot of lead, which is synthesized, barium, europium, and also thorium and uranium. But of course, and this is something I wanted to mention as well, there are some uncertainties, and among them you have nuclear uncertainties. And this is a study that was done by Sébastien Martinet, a postdoc here in Brussels. What you see here is like 50 different AGB models, the same one. So it's a one solar mass star at metallicity, at low metallicity. And in each time we computed 50 different sets of N-gamma rates. The detailed procedure is explained in this paper, but the idea here was to try to see the extent of the nuclear uncertainties. And you see the results are shown by the different points, and you see the envelope, which is like the lower envelope is in blue and the upper in red. And on the bottom plot, you see that the typical uncertainties are typically between 0.5 and 1 dex, the nuclear uncertainties. So it's not, it's already something. But if you look at thorium and uranium, the uncertainty are very large, actually. Depending on the set of N-gamma rates, you can either have no thorium or no uranium or a lot. So this is like some big challenge, I would say, to try to maybe understand a bit better if indeed the eye process can or cannot make these very heavy elements, because of course it's very, as I mentioned, the threshold value is 10 to the 15, 10 to the 14, and we are really at this threshold value. So depending on the nuclear reaction rates, you can just cycle in the lead region or go very high and synthesize these elements. So I'm almost done. This was just to show like some yields of AGB models experiencing proton ingestion. I think it's also something I wanted to make that. So you have 4 elements here: strontium, barium, europium, and lead. You see the x-axis is the metallicity, and the different dots are different models with different initial masses. And something I wanted to show is also that if you go to high metallicity, even if you have proton ingestion, you will not synthesize heavy elements. As you can see here, when you go to solar metallicity or near solar, you see that the yields of strontium, barium, lead, etc. is very small. And this is because of the neutron to seed ratio, which is decreasing, of course, at this very high metallicity. You have the same at solar metallicity, let's say. If you have a proton ingestion, you have a lot of iron compared to low metallicity, but you still have the same amount of neutrons. And to make it the story very simple, this iron, which is very abundant, will take all the neutrons, and it will prevent the synthesis of barium and heavier elements. So this is the main idea. So there are different places where high process yields can be found, not a lot. There are accreting white dwarfs here by NuGrid, and also I think, of course, there is the Fruity database with many S process models, and also I think a few I process models. And we are also trying to compute these models. So there is these models from Starevol in Brussels. And maybe to finish, a question also we can have is, how does it compare? So if we take these publicly available yields from the rapidly accreting white dwarfs that I was mentioning at the beginning as a potential site for eye process, so is it very different than the eye process that takes place in AGB stars? Actually, it is very close, so at least in these 2 models. So again, I took one star, which is a kind of reference possible eye process star. And if you try to reproduce this star with an eye process model from an accreting white dwarf, you have this red pattern and you have this black one with the AGB model that we computed here in Brussels. So at least if we consider these two models, you see that, of course, there are some differences because probably the nuclear rates are not the same, the conditions are not exactly the same, but it is striking to see that the nucleosynthesis is very similar in these two models, even if they are quite different, actually. Huh? It's like accreting white dwarfs and AGB stars. An idea could be to try to disentangle and to see maybe some differences between models, would be to try to look at isotopic ratios, maybe light elements. So yeah, honestly, I didn't go into details, but this is maybe the occasion to mention also the fact that if you have proton ingestion in AGB stars, at least, you produce a lot of lithium. So in the top right, you see the lithium surface abundance before proton ingestion and after the proton ingestion, and it's quite high after. So there is an enrichment of lithium thanks to the Cameron and Fowler mechanism that can produce a lot of lithium in the star. And also there is a big production of C13, which decreases the carbon over C13 ratio. So this is before and after the proton ingestion, the bottom left plot. So the I process in AGB comes also with a low C12 versus 13 ratio and some lithium. Okay, I will stop here and maybe try to summarize. So in part one, I was saying that the I process is a neutron capture process that can synthesize heavy elements, and one possible site are the AGB stars. There are different possible sites as well, and actually we don't know what is the site of the I process. If the I process exists, we don't know what is the size of the size. Yeah, if there is one of different sites. There are I process stars that support the existence of this process. The AGB stars can host the S and I processes, and this I process can develop when protons are ingested in the convective thermal pulse. Actinides can be produced by the I process, depending on the nuclear rates. The proton ingestion can be obtained up to, even in solar metallicity stars, if overshoot is included. I would say a rather strong overshoot. But the I process signature vanishes at high metallicity. And yeah, there are some nuclear uncertainties, especially for thorium and uranium, which are very high. There are many next steps and also open questions, including what is the I process sites, as I said, and their relative contributions. We still don't know. I think there are many candidates, but we still don't know. How strong is the overshoot in AGB? This is really linked to what I was saying, and maybe here 3D hydro models would be needed. We don't know the effect of rotation or magnetic fields on the I process. This was done in AGB stars for the S process, for instance, in these papers here, but not for the I process. Galactic chemical evolution models, there is just one, to my knowledge, paper that includes I process models in galactic chemical evolution. This was this paper from Cote that includes some accreting white dwarfs. And also, we really need some new experimental constraints on the N-gamma rates to improve the predictive power of these models. So thank you very much, and I will take any question.
Thank you, Arthur. Thank you very much for being in perfect time also. Are there any questions? If so, please just unmute yourself.
Oh, okay, if there are no, could you hear me?
Yeah, there is one question from Sergio also, but you can go also.
Ah, okay, Sergio, go ahead.
Go, Oscar.
Okay, so I have two suggestions for your future works. The first one concerns the fact that when you have these proton ingestions during a thermal pulse, no? When the convective shell extend up to the top of the Inyo-rich regions and can bring some proton from from the envelope inside, actually you have at the bottom, you are near the maximum of the extension of the shell of the thermal pulse.
Yeah.
When the temperature at the bottom are of the order of in between 300 millions of Kelvin up to 400 millions of Kelvin, it depends on the core mass. No. When the proton ingestion starts, you move this proton inwards, but actually they do not never reach the bottom of the convective shell, but they burn on fly.
Yeah.
Typically, they burn when the temperature is around 200 megakelvin, 200 millions of Kelvin. Why? Because at that temperature, if you compare the mixing time scale with the burning time scale from the carbon-12 plus proton reaction, for instance, which is the most rapid one, these occur more or less at this temperature. So somewhere in the middle where this temperature is attained, 200 millions of Kelvin degree, you have a release of energy, a local release of energy, thermal energy, of nuclear energy, and this hydrogen flash produce a peak in the temperature and in the entropy. So what happened is that you expect a splitting in two convective shells separated by a thin radiative region. The internal one, which is driven by the triple alpha, the typical thermal pulse. The external one, which is driven by the hydrogen flash. The problem, what is the problem? Is that in the external convective shell, you continue to engulf protons. So you form carbon-13, but you also form a lot of nitrogen-14. And if you follow this process, you should find that at the end you have more nitrogen-14 than carbon-13. This is a problem because even if you have enough carbon-13 to activate the carbon-13 alpha N, the nitrogen-14 is a neutron poison. So almost all the neutrons produced by the carbon-13 alpha N are captured by the nitrogen-14, and so at the end you have limited production of heavy elements. That's the first point, and the splitting is confirmed by the 3D hydrodynamical models. Now it is clear that this should actually occur. So that's the first question, the first point. The second point concerns the lithium production. Yes, it's true. These stars that undergo the proton ingestion should be enhanced in lithium. But this is not the Cameron-Fowler mechanism. This is a completely different scenario. Because when you have the proton ingestion, you also ingest helium-3 from the top.
Yeah, exactly.
And this helium-3 reacts with helium-4, forming beryllium-7. So at the end, in this helium-rich region, you have beryllium-7. But beryllium-7 plus, and the proton are captured by something else. So the beryllium-7 plus proton reaction is not very active. The time is too rapid to have electron capture, and the temperature is large enough that you don't have beryllium with the K shell, electron K shell filled to have the electron capture, as it happened in the sun, let's say. So actually, this beryllium-7 remain there. So when everything finish, you have this beryllium-7 there that have plenty of time to stay there. And then when you have the dredge up in the following time, when you have the dredge up, this beryllium-7 and is brought to the surface and then can decay into lithium-7. So it is a little bit different with respect, no, a little bit, it is substantially different with respect to the classical Cameron-Fowler mechanism. It says that, and it is a typical feature of the proton ingestions. So in general, a general comment may be that when you have proton ingestion, not necessarily you may have production of heavy elements. So proton ingestions and I process are not synonymous. But in some case, you may have the I process. In some other case, you may have lithium production. You may have low carbon-12 on carbon-13. Yes, that's true, but not necessarily the I process. This is quite controversial.
Yeah. So these are very, very good points, actually. So about the second point, so so about the lithium. So no, first about the correspondence between I process and proton ingestion. That's right. And I said that to have I process, you need a proton ingestion. But indeed, if you have proton ingestion, you may not have I process. And for instance, if you look at just these yields, this is what's happening here at high metallicity. You don't have any I process happening, but you have proton ingestion. So there is not. It's not equivalent, I would say. So this I really agree with you. And I might have said the contrary, but indeed it's not the same thing. It's not an equivalence. Secondly, the lithium. So it may be a bit different. So this it might be not exact what I have written here. So this is maybe not the same mechanism. Honestly, I don't remember in details exactly how the Cameron and Fuller mechanism. So this, I will check it again, and maybe you are probably right. So this is a good point. But
the trick is to form beryllium-7 in a proton exhausted region. No, so if you have a proton, even if the temperature is quite large, but you cannot burn this beryllium-7. Because you don't have the protons to react. So that's the trick.
So the helium-3 is ingested here. You see in this plot here, and the beryllium-7 is synthesized so quite quickly. And there is this after the split. So I will come back on the split after, because it's a really important point. After the split here, the temperature at the bottom here is quite low. Is maybe if you take the upper part of the convective zone, the temperature at the bottom is less than 100 million degrees or something like this. So it's quite low. And if I remember well, and we wrote last year a paper really focusing on the production of lithium. The lithium is produced here, so the beryllium is really there is this electron capture reaction taking place and forming lithium. So beryllium that capture electrons to form lithium-7, and we have updated the rate as well to check. And it takes place really here. And this is really here that the lithium is synthesized, and this stage is lasting for a few years. From here to the merging with the envelope, it's about 10 years. So it's quite quick, and there is time here to for this beryllium to decay or to capture electrons and to form lithium, and the lithium to go up. So probably this is what you said, and maybe the main point was to say that it's not the same thing that the Cameron and Fuller mechanism, and probably that's the case. So maybe the last point about the split, but because it's really important. This was your first point. So I didn't mention the split because it's quite technical, but it's indeed extremely important because, of course, it is confirmed by 3D models, except if you check, for instance, the paper by Stancliffe in 2012 or 11, they don't find a split, for instance, in 3D models. So maybe the resolution was not large enough, but it's not always the case, I think. But in general, yes, the split is something which is, I think, really observed and noticed even in 3D models. And in all of our models, we have a split, actually, because of exactly what you said. So the release of energy by the C12 P gamma reaction. So here, by the way, we have to couple the diffusion and the nucleosynthesis, because, of course, the mixing time scale is the same as the nucleosynthesis time scale or the burning time scale of the protons. So in this location here, so I don't know if you see my pointer, but here, this is
unfortunately no, but we can understand what you are saying.
Yeah, so it's really here there is a point where there is a strong release of energy, an inversion of the temperature gradient, and then a splitting of the convective pulse, and then from the splitting, nothing happened in terms, at least in our models, in nucleosynthesis of heavy elements in the upper part of the pulse. So I mean, if you take the upper part of the pulse after the splitting, nothing is happening in terms of nucleosynthesis of heavy elements. So If there is some nitrogen 14, it is the case probably, and this will be a strong poison, of course, but all the I process, at least in our case, is really taking place here at the bottom before or after the split. And the problem is that if it takes place after the split, it will stay locked into the star and probably will never reach the surface. And this is really depends on of course, of the details of the models. But in general, we have really checked into details that the mixing time scale here is short enough to when the I process are produced at the bottom of the pulse, the mixing time scale is short enough to bring up this material before the splitting. And then this I process will be, I would say, saved and could reach the surface. But I mean, there is no, I think you said that this from what I understood, at least in this upper part of the pulse, the temperature is very low, and it's actually much like close to, I would say, maybe 100 million degrees, and it's not enough to activate like this C13 alpha N reaction in a time scale of about 10 years. So nothing happening is happening here. Yeah, okay, I speak too much, but I think we agree in general. It's just to make some precision.
Thank you, Arthur, for your answers. I think that if there are no other questions, unless Sergio has a very quick one.
No, okay, it was just a comment, but nothing really helpful to the discussion already, let's say, stressed by Oscar. We can discuss this in Giulianova, Arthur.
Sorry.
Okay, we can continue to discuss about that.
Yeah.
It's very interesting.
Yeah.
Okay.
So then we can thank again Arthur, and
Thank you very much.
thank you all for have participated to the seminar.
So
Thank you, Arthur.
Thank you very much.
Bye-bye.
Goodbye.
Ciao. Ciao.
Our next meeting is in 9 days. Stefano Di Frisca will talk about artificial intelligence. That's it. Ciao.
Ciao a tutti.